You're lucky this is twice down. Double my tuition. I think Shelby has a leg injury softball this morning. Not Shelby, Isabel.
Okay. Sorry to hear that. I remember last semester she got pumped in the head, and that was pretty bad.
Softball.
Yeah.
She was getting sweater. Terrible.
Okay, we're going to go ahead and get started. Can the people on Zoom see the slide and hear me okay? Okay, thank you. Okay, so what we're going to do today is we're going to finish chapter 24, which is the organic chemistry, biochemistry section. And then we will have a quiz on this chapter on Thursday of this week. On Thursday, there will be no lecture, so it'll just be the quiz. So just on Thursday, go ahead and log on to Canvas and take the quiz. I will warn you that the quiz will have less time than normal, just because there's no math on this quiz. It's just kind of, did you memorize a bunch of stuff or not? And I don't want people just looking everything up. I wanted you to really kind of see if you learned some of the stuff in that. So the quiz time will be a little more limited than normal for that reason. So just be ready for that. The other thing I wanted to mention is next week on Tuesday, we'll have our last lecture. That'll cover some nuclear chemistry stuff. And then on Thursday of next week, we'll have exam number 5, and that'll cover chapter 24, the stuff we're finishing today, and then the nuclear chemistry stuff, chapter 21. And then the week after that will be our final. So we're kind of getting to the end of things. So, you know, try and keep studying and finish strong with the last couple of quiz and tests, and then the final exam. So I'm going to go ahead and get started here. And we're going to pick up with alkenes. So previously we talked about alkanes, which was carbon and hydrogen containing compounds that were all single bonds. With alkenes, we start introducing double bonds into it. And so hopefully everyone remembers what a double bond is from earlier in the year. But the key thing about double bonds is instead of having that sigma bond, which we see in the single bonds, which is a pretty strong bond, it also has a pi bond. And it's that pi bond, that gives alkenes some reactivity that we didn't see with the alkanes. So you have those pi electrons, and that makes a difference. So in terms of naming these compounds, there's some similarities with how we named alkanes. One is we're looking for the longest chain, just as we did with the alkanes. But the difference here is both of the carbon atoms that are involved in the double bond have to be part of that chain. The other thing is we want the carbon double bond, the carbons involved in the double bonds, we want those atoms to be the lowest number that they can be. So if our choice is 1 and 2 versus 6 and 7, we're going to pick 1 and 2. And then B end with ene. Okay, one of the things we start introducing with double bonds, because there's not much rotation around that double bond, we start to get what's called geometric isomers. And so what that means is that direction of the longest chain can differ when you have 4 more carbon atoms. And we start introducing a 3-dimensional arrangement of these geometric isomers. And one of the things that we'll see in a moment here is what's called a cis and trans configuration. And what cis and trans mean is if you have the 2 carbon atoms that are involved in the double bond, and you have groups that come off of those carbon atoms, when you have things that are on the same side of the double bond, that's cis, and when they're on opposite sides, that's considered a trans isomer. It's probably a little easier to visualize that with the picture, so let's go and take a look at that. And let's focus on the 2 structures on the right-hand side of the slide. If we look on the first one, the cis-2-butene, we see the longest carbon chain is 4, and we see carbon atoms numbered 1, 2, 3, and 4. We see our double bond carbon atoms are labeled 2 and 3. And then next to it, we see what's called trans-2-butene. And so once again, we have 1, 2, 3, 4. The longest carbon length, chain length is 4. And we see the double bonded carbons are labeled 2 and 3 number carbons. And so both of these are 2-butene. But now we start seeing that geometry being a little different in terms of the spatial situation. And the one on the left, the 2 methyl groups, the 2 CH3 groups, those are both on the same side of the double bond. Next to it, we have the 2 methyl groups where one is on top and one is on bottom. And so now that configuration is called trans. So this idea around double bonds of where things are on the same side of the double bond, it's cis. If they're on opposite sides of the double bond, it's trans. That's something I would expect you to know and be able to identify in these cases here. So I'm going to move on from there to alkynes. So alkynes, remember, are where we have a triple bond present. And with a triple bond, it means we have a sigma bond and then we have 2 pi bonds. We also start introducing a term called unsaturated. Unsaturated, so if something's saturated, it means it has the maximum number of hydrogens. In this case, we don't have the maximum number, so it's called unsaturated. The naming convention is similar to what we did for alkanes and alkenes. We look for that longest continuous carbon chain, and that's our base naming convention. And then we need to make sure, just as with the alkenes, that the 2 carbon atoms, in this case, that are involved in the triple bond are in that longest chain. And just as we did with the double bond carbon atoms in the alkenes, the triple bond carbon atoms, we want those to be the lowest number carbon atoms that we can have. So in other words, once again, if we have a triple bond, we would want it 1, 2 rather than 6, 7 if we were going to do a naming. Remember, alkanes ended in A-N-E, alkenes ended in E-N-E, and alkynes end in Y-N-E. So if you see that Y-N-E, that should tell you got a triple bond somewhere. E-N-E, a double bond somewhere, and A-N-E, it's all single bonds. The alkanes don't react much. Remember, we said the alkanes can burn, we can have that combustion reaction. But because of the pi electrons, we can have some reactions with alkenes and alkynes. And 3 common reactions are hydrogenation, so in other words, reacting with H2, reacting with water or hydrogen halides. Remember, a halide, a halogen is chlorine, fluorine, things like that. And then finally, a halogenation reaction where you're reacting with one of those halogens. And once again, we can have those kind of reactions because of that, the pi bonding in these alkenes and alkynes, and the availability of those pi electrons versus just sigma bonds in the alkanes. Here's some examples of those reactions. What you'll see is the reactivity always centers around that double or triple bond, and that's what we see in these examples. The first where the bromines are added. The second was where protons are added. Same as in the third one, we're having a hydroxyl group added. And so it all centers around that. And then finally, the last one is chlorate, another halogen reaction. But we see in all of these cases, the key is having that double bond or triple bond and those pi bonds and pi electrons available. So one thing that is a little different though, is when we think about the aromatic hydrocarbons, remember that's the benzene ring type of thing. And so in that case, we have pi electrons, but if you think about the benzene ring, when we talked about it in the past, one of the things we talked about is how even though sometimes it's drawn with alternating double bonds, that's not really what's going on. There's more of what we call a delocalization of the electrons. In other words, the electrons are kind of smeared out and around all those bonds and kind of shared. So whereas with the alkenes and alkynes, you have a more defined pi bond. In this ring structure, it's this delocalized type of situation, so it's not as structured. Because of that, those electrons are a little less available, and so they're less reactive than what we see in alkenes and alkynes. You do get some reactivity going. In this case, it's a substitution reaction where you replace the proton on the ring with whatever the group is. Three that you do see are nitration, halogenation, and alkylation. And so let's take a look at a couple examples of those. So we see the nitric acid reacting in the first one to form nitrobenzene. In the second, we have bromine reacting to give us bromobenzene. And then finally, we have the alkylation in the third, where we get ethylbenzene. So you do get some reactivity with the aromatic rings. I think that in this drawing, we've drawn the benzene ring with the circle in there. I think that's a little better reflection of what's really going on with those pi electrons in this case, rather than the alternating double bonds. So some reactivity with these, not as much as with the double bond and triple bonds of the alkenes and alkynes. Okay, so there is something about the aromatic nomenclature I want to make sure everyone is familiar with and knows. And so when we talk about naming these benzene derivatives, and let's focus on this example of the nitrobenzenes here in the middle. And so we see in the first figure, we have our benzene ring, and we have it labeled 1, 2, 3, 4, 5, 6 in terms of the carbon numbers. And we see a nitro group on the 1 and 2 spots. So we could call that 1,2 dinitrobenzene. The second one, we go through and we see now that second nitro group is on the 3 carbon. So we could call that 1,3 dinitrobenzene. So we have our benzene base, we have 2 nitro groups, so we have di, and then the group, as I said, is the nitro group, and then the location being the 1 and 3 carbons. And then finally, the fourth one, we have nitro groups on the 1 and 4 carbons, so we have 1,4 dinitrobenzene. But what is done for these types of ring substitution compounds, where you have these substituted benzenes, is people will use the 1,2 or 1,3 or 1,4 convention, but they also will use ortho, meta, and para. And so if we go back and look, we see that when it's in the 1,2 position, that's also called ortho dinitrobenzene. When it's in the 1,3 position, meta, dinitrobenzene, and the 1,4 would be para-dinitrobenzene. So in chemistry, there's always kind of like the official name, and then there's some of these, what they call common names. And usually one or the other is the preferred. I would say that when it comes to these ring structures like this, neither one is preferred. You're just as likely to see 1,2-dinitrobenzene as you are to see ortho-dinitrobenzene. So this is one where the expectation is that you will learn that 1,2 is ortho, 1,3 is meta, and 1,4 is para, because it's never certain how they're going to name it. And so you need to know both ways. So once again, if they're next to each other, it's ortho. If there's one space in between, it's meta. And if there's the two spaces, then it's para. So we've talked about the alkanes, we've talked about the alkenes and the alkynes, and even this benzyl type group stuff. But really, that's all pretty simple stuff in terms of organic molecules. Organic molecules, the chemistry gets much more involved and much more interesting when you start talking about something called a functional group. And a functional group is really just a combination of atoms that are stuck onto a base molecule. And a couple things about this. You'll often see this capital R. And the capital R just typically represents some type of alkyl portion. Alkyl is some CH type portion of a molecule. And the example we have here is ROH. The OH, that's called an alcohol group. And then the R just means there's other stuff on there. So it's kind of like a generic catch-all thing. So you'll see that sometimes that people will write. What we're going to go through now is we're going to go through some of these functional groups. And the expectation is that you'll know what the functional groups, what represents what functional group. And then if you were given a molecule, you'd be able to say, oh, what kind of functional group does that molecule have? So one of the things you're going to have to do is, we'll look at a table here that's got a bunch of functional groups. One of the things you're going to have to do is basically just memorize that table. Memorize what the functional group name is and what it generically looks like, so that then later you can pick it out of real compounds. So let's start looking at this table. And we're going to focus over here on the left-hand side of things, and then on the structural formula or the main things. The suffix is important because that helps you with the naming. But let's start with the first one. So we have C double bonded to C. We just covered that, so hopefully you're saying that's an alkene. Then a C triple bonded to a C. So that carbon-carbon triple bond, that's an alkyne. And then the third one on this slide is a carbon single bonded to an oxygen, which is single bonded to a hydrogen. So this OH is called either an alcohol group or a hydroxyl group. Those terms are used interchangeably. So if I say it has an alcohol group on it or a hydroxyl group, what I mean is this OH group is bonded to it, in this case to the carbon. And we see when for that alcohol type of compound, it's going to end in OL. So we have methanol as the example. Methyl alcohol is the common name. So those are kind of similar to what we've been talking about. Now we're going to branch out a little bit for some other functional groups. The first one is called an ether. And so what we see with the ether is we have an oxygen atom, and then we have a carbon on each side. So we'll talk about the ethers in a little bit, but in general, if you see this where it's a chain and there's an oxygen sandwiched between two carbons and there's nothing else coming off that oxygen, in this case, you see we have lone pairs of electrons. but no atoms coming off of it other than those carbons. That's an ether. The next is carbon with a halogen. And remember, halogens, once again, are chlorine, fluorine, bromine, stuff like that, that column in the periodic table. Those are alkyl halides, and they end in IDE, ide. And then the last one on this slide is an amine. And what an amine is, it's a compound that has this nitrogen atom in it. So this nitrogen atom, in this case, it's connected to a carbon, and that's typically how it is. And then you have two other spots where things can go, and we'll talk about amines in a little bit. But the thing to remember is amines have nitrogen in them. So if you see the compound and it's in that organic type of situation, so we're not talking about nitrites or nitrates or anything like that. We're talking about in the context of an organic compound, then it's an amine. And those name convention is pretty easy because you just tack on the word amine to that when you name it. And the reason why all these functional groups are important is when you think about reactivity of organic molecules, the reactions are usually centered around these functional groups. But a little bit of exception, like with that double and triple bond stuff that we just talked about. But in general, it's these functional groups where the reactivity occurs. Now we're going to talk about a series of functional groups that have something in common. And what they have in common is this carbon double bonded to an oxygen. And carbon double bonded to an oxygen like that is known as a carbonyl group, okay? So what all of these next few that we talk about are going to have in common is they're all going to have a carbonyl group. And so the first one, we have our carbon-oxygen double bond, and off the carbon to the one side is a hydrogen atom. So if it has a hydrogen atom bonded to that carbonyl carbon, and then the other side would be that R group that we talked about, then if that or something similar, then in that case, it's what's called an aldehyde. Carbonyl carbon with a hydrogen bonded to it, aldehyde. The next one, carbonyl carbon with carbons on each side. Excuse me. Carbonyl carbon with carbons bonded to it, two carbons bonded to it, that's a ketone. And then finally, the third one on this slide, carbonyl carbon with an OH bonded to it, so an oxygen and then a hydrogen bonded to that oxygen, so that an OH group or hydroxyl group, that's a carboxylic acid. In the naming convention, the aldehyde ends in AL, the ketone ends in ONE, and the carboxylic acid ends in OIC. So all these have the carbonyl group, that's that carbon double bonded to an oxygen. If the carbon has a hydrogen bonded to it, it's an aldehyde. If the carbon has two carbons bonded to it, it's a ketone. If the carbon has a hydroxyl group bonded to it, it's a carboxylic acid. The carboxylic acid, that proton, that hydrogen atom on the carboxyl group, that is a real labile hydrogen. It can easily be donated, or it can stay on the carboxyl group. It just depends on the pKa of it. Remember, Ka's are acid dissociation constant, pKa's minus the log of that. So that gives us a feel for how easily that proton either stays on or comes off. And then depending upon the pH of our solution, we can control what that proton does. The last two that have this carbonyl thing that we want to mention is the first one has our carbonyl carbon and oxygen, so that's C double bond O. It has an oxygen bonded to that carbon, but instead of that proton, that hydrogen atom, to the oxygen, like we saw with our carboxylic acid, it now has another carbon, and that's considered an ester, okay? It's a real common reaction to take carboxylic acid and do an esterification reaction and put this alkyl group on it. The last one, we have the carbonyl group. So we have that carbonyl carbon, the double bonded oxygen to it. And then we have a nitrogen. So this is called an amide. And so this amide functionality, this is real big in the biochemistry world. So when we get to the part where we're talking about peptides and things like that, we'll talk about peptide bonds. And this carbonyl carbon bonded to a nitrogen, that's that peptide bond that you hear about in proteins and peptides and things like that. So we'll get back to this a little later this morning when we get to the biochemistry section a little bit more. So once again, we go back, there's quite a few of these in here. The expectation though is that you'll be able to recognize and identify functional groups and what type of compound it's associated with it. Okay, let's go into a little more detail on each of these just to give you some examples. As I said before, alcohols contain that OH group. That OH group is also called, in addition to being called an alcohol group, is called a hydroxyl group. And here's a couple of examples. So to name it, we still have that same idea of having the longest base chain we can have. And then we also have the bit of where we want to locate where the OH group is. And then we want to end it with an OL. So if we look at the first example here on the slide, we see we have CH3, CH, CH3, and an OH group coming off the CH. 3 is the longest carbon chain, so that's prop. We have OL for the alcohol, and we want to give it a location, and that's the number 2 carbon. So it's 2-propanol. The next one we see, the other thing I'll comment on that is 2-propanol would be kind of like the official name, but you can also see that CH3, CH, CH3, that's an isotype group, so it could also be called isopropyl alcohol or isopropanol. The next one, once again, we get 3 is our longest chain. We can call that 2-methyl 2-propanol. So giving us our location of our methyl group and our hydroxyl groups of the 2 carbon. And then the third one, 1,2-ethane diol. When you have 2 alcohols on there, that's a diol. And so we're told that diol tells us there's 2, and it's on the 1 and 2 carbons. Okay, ethers, remember we said ether was where that oxygen is in the middle of R groups, in the middle of carbons. So there's not that, it's the way you remember ether is the one that doesn't have the double bonded oxygen. That's probably the easiest way to remember that. Ethers in general aren't real reactive, and that's why they're often used as solvents in organic reactions. And here, down at the bottom, we have 2 examples of common solvents that are used in organic reactions. The one on the left is diethyl ether. So we've got 2 methyl groups, diethyl, and then it's an ether. And then the one on the right, tetrahydrofuran or THF, a 5-member ring there. So once again, ethers have that oxygen, but the oxygen's not involved in a double bond or anything like that. So let's now spend some time focusing on the functional groups that have that carbonyl group. As we said, the carbonyl group is that C double bonded to oxygen. And there's 5 main things functional groups that we'll talk about. And these are important to know because, as I said, a lot of reactivity occurs around these types of functional groups. So we want to be able to tell the difference. Aldehyde, again, if we see this carbonyl carbon with a hydrogen attached to it, aldehyde should come to mind. And here's 2 examples here. For both of these, the official name is methanal, ethanal. The one on the left is formaldehyde. The one on the right is acetaldehyde. I don't think in my life I've ever heard anyone call it methanal, ethanal. They use the common names formaldehyde and acetaldehyde. I wouldn't worry about that. I think what I would worry about is being able to recognize that these are aldehydes because I see that proton attached to the carbonyl carbon. Below, we have some examples of ketones. Propanone here on the first one, and 2-butanone on the second one. Once again, we see the common names of acetone and methyl ethyl ketone here below it. This is another example where the common names are really what you are more likely to encounter. But once again, the thing to take away on this is, how do we know it's a ketone? It's a ketone because we've got a carbonyl here in the middle, so this C double bonded to an oxygen. We've got that carbonyl group, and the 2 things that are attached to that carbonyl carbon are alkyl groups. So no hydrogen. If one of those was a hydrogen, it'd be an aldehyde. Since neither of them are hydrogens, it's a ketone. So aldehydes and ketones, important to know the distinguishment between those 2. So next, let's go to carboxylic acids. And so once again, we have that carbonyl group. So we have that carbon double bonded to the oxygen. And then attached to that carbon is the hydroxyl group, the OH group. The other thing about, as I mentioned before, about these carboxylic acids is they're weak acids, and that means you can donate that proton can leave off of that OH group. And so, depending upon the pKa of it, that tells us how weak or strong of an acid that the particular carboxyl group is. Let's take a look at a few examples of this. So, first one, lactic acid. This one's interesting because we have 2 OH groups in that. So the OH group on the right in blue, this is part of a carboxyl group because we have our carbonyl, our C double bond O, and the hydroxyl group is attached to a carbonyl carbon. So that tells us that's a carboxyl group, and this proton on the carboxyl group, that's pretty easy to donate. The other OH group, the other hydroxyl group, that's attached to a CH. So that is an alcohol there. And that proton is much more difficult to donate. That's a pretty stable, alcohols tend to be pretty stable. So here's a case of where 2 different OH groups, but because of what they're attached to, very different properties. The one in blue, carboxyl group, the one in black is an alcohol group. We see methanoic acid, that's usually referred to as formic acid, and then citric acid, that's the acid in citrus fruits. And so what you see here with the citric acid is interesting. Citric acid is what's called a triprotic acid, because you see in blue, we have 3 carboxyl groups, okay? The blue ones are carboxyl groups. The black OH here off the carbon, that's an alcohol group. So these carboxyl groups, 1, 2, 3 of them, this compound actually has 3 pKa's for the ability to deprotonate each of those carboxyl groups. They're different. They don't all deprotonate at the same pH. So carboxylic acids, there's some other stuff listed on here you can take a look at. But carboxylic acid, we have that C double bonded O carbonyl group and the functionality, and then we have an OH bonded to the carbon. Okay, esters. Esters are, in my mind at least, real similar to the carboxyl group that we just talked about. Because what we have is, we have that carbon double bonded to the oxygen, carbonyl again. And then to the one side, we have an oxygen. So once again, we have oxygen bonded to that carbonyl carbon. The difference is, bonded to that oxygen isn't hydrogen, but it's some alkyl group. In this case, in this example here, it's an ethyl group. So esters, for the most part, come from reacting with a carboxylic acid. And so by reacting, you put this alkyl group in the place of where the proton was. Bullet point 2 on this slide says a lot of esters are found in fruits and perfumes. What's interesting about that is, what do fruits and perfumes have in common? They both smell, right? Usually it's a nice smell, but it doesn't have to be. And you think about that, what do you have to have? What property does a molecule have to have for you to be able to smell it? Well, it's got to be volatile. If it's not volatile, you don't smell it. One trick in chemistry that's done is carboxylic acids in general aren't very volatile. If you want to do an analysis and you want to do it to where you want to volatilize them, it's a real common reaction to make an ester of it. In this case, ethyl ester, oftentimes it's a methyl ester. When you make those esters, the compound that before wasn't very volatile usually becomes more volatile. And so that kind of fits in that a lot of these esters are found in fruits and perfumes, because when we think of those things, we think of things that smell good, have a nice smell, but the key thing is it's something that you can smell, so the compounds are volatile. So esters, remember, are similar to the carboxylic acids with the C double bonded O and then a single bonded O to a C, but then instead of the hydrogen on that single bonded oxygen, you have some alkyl group on there. Methyl esters, probably the most common, in this case, an ethyl ester. Okay, we said earlier that if a compound has a nitrogen in it, then we call that an amine. And so we want to just refresh ourselves a little bit on that. And so once again, here we have ethylamine, trimethylamine, and phenylamine, also known as aniline. The first one, because we have one R group, that's called a primary amine. The second one, we have 3 R groups, so that'd be a tertiary amine. And then this last one, this phenylamine, since we have 1 R group, that would be a primary amine also. So amines are either primary amine, secondary amine, tertiary amine, and once again, if they have 1 R group, it's a primary amine, 2 R groups, secondary amine, 3 R groups, tertiary amine. You can also have a quaternary amine where you have 4 groups on it, but then the amine becomes positively charged. I'm only mentioning that because in the world of COVID, where everyone wants to disinfect, there's a class of compounds called quaternary amines, and a lot of times they're just called quats. And if you look on a lot of the cleaning products to disinfect, that's what they have in them, are quaternary amines, quaternary ammonium compounds. We wanted to just refresh on the amines a little bit, because this is going to lead us to, sticking with our carbonyl theme, lead us to that amide formation. And so we see that down at the bottom here. And what I would ask you to look at is, on the right-hand side of the equation, in blue, we have CH3, then a carbonyl group, then a nitrogen, and then 2 methyl groups onto that nitrogen. This thing in blue, the portion in blue, with the C double bonded to the O, and then the carbon bonded to the nitrogen, that is our amide. Okay, so if you have carbonyl carbon bonded to a nitrogen, we call that an amide. And as I said before, a little later, we'll see that amides are a big deal in the biochemistry world in particular. So we went through that table and talked about different functional groups. Then we kind of followed up with those and gave a little bit more in terms of examples and talked about them again. So if you're thinking about studying for the quiz that you're going to have on Thursday, make sure that you're comfortable looking at a molecule and deciding, is that an ester, is it an ether, is it an amide, what kind of functional group are we seeing in that molecule? Okay, the expectation is that you could do that without looking it up. Okay, so one of the things that we often see in organic chemistry is we have a carbon that has 4 different groups bonded to it. Okay, so instead of having, say, 2 hydrogens and then a couple other things, or something like, or 2 methyl groups and then some other things, each of the bonds on that carbon is bonding with a different group. When we have a carbon that's bonded to 4 different groups, then we say that that is a chiral carbon. And that leads us into the discussion of chirality. And why is a chiral carbon important? Well, because if that carbon has the 4 different groups attached to it, then we have what is called optical isomers. Okay, and the easiest way to think of optical isomers is if you're in a 3D type situation. So if you had a little model building kit and you built the model of each version in terms of arranging those 4 atoms around, those 4 groups around the carbon atom, what you would find is, even though you've got the same atom, the same groups attached to that carbon atom, you're not going to be able to superimpose those. And that's where people say you have mirror images. And so that is what you're talking about with these optical isomers or enantiomers. And so they have the same molecular formula, they have the same things bonded to that carbon. It's just the spatial arrangement is different. And because of that, the end result is, and this is how you tell these, is they rotate light differently. So there's something called a polarimeter, where you shine light on it and then the light will make it go either left or right. And based on that, that's one way you can tell if you can tell which isomer you have. The other thing about a couple other things I want to mention about chiral carbons. So when you have the exact same amount of the 2 optical isomers, the 2 enantiomers, then that's called a racemic mixture, okay? And that's actually one way you can tell is if you have a racemic mixture or not by how a solution of the material polarizes the light. And the other thing I want to point out is, let's look at the second molecule on the slide, not the top one, but the one below. If we look at this molecule, if we focus on the right-hand side, we have a chiral carbon there. How do we know that? Well, we have a carbon And if we look at the two kind of wedge-looking bonds, the dark filled-in one is a methyl group. The one with kind of a dotted wedge is a proton, a hydrogen atom. The other one going straight up, a normal-looking bond, that's a carboxyl group. The one to the left is a phenyl ring. So 4 different things on that carbon, okay? That's our definition of a chiral carbon. When you have these chiral molecules like this, the dark colored wedge and then the kind of the dotted wedge, those are meant to impart like a 3D to the thing. So obviously it's a 2D picture, so you can't draw 3D and 2D. But by having the colored wedge and the dotted wedge, you're saying one of those goes out of the plane of the paper and the other goes back behind the paper. And that gives you that 3D image there. And that's the way that people will express chiral carbons, okay, is by having some of that 3D on there. So the couple takeaways on the chirality stuff. If the carbon has 4 different groups on it, it's a chiral carbon. And then if it's a chiral carbon, that means you have an enantiomers. So in other words, you can reflect light one way or the other, is the way you think of it. And if you have equal amounts of those 2 enantiomers, then it's a racemic mixture. Why is this important? Well, first of all, it's not unusual for a drug, and by drug I mean a pharmaceutical product, to be chiral. I've also seen this in agricultural chemicals as well. And so if it is has a chiral center, and some compounds have more than one chiral center, and then it really gets complicated. But we're not going to worry about that for now. What has been found is, because a lot of the mechanisms that occur in the body and in nature and that depend on not only what the atoms are in the molecule, but the actual 3D structure. You know, a lot of times we lose sight of the fact when we write these on a piece of paper, that that's really a 3D molecule. And a lot of it is just the geometry factors into if it's going to be effective or not. So it's not uncommon to have enantiomers, and one of the enantiomers works great and the other one doesn't do anything. Or even worse, one of them works great and the other one has some negative properties, so some hazardous properties. So if that's the case, it's very important you know which enantiomer is which and which one you have and things like that. So there's actually a thing in analytical chemistry called chiral chromatography, where people go through a lot of effort to physically separate the enantiomers so you can figure out how much of each you have and isolate them so you can test which is the good and which is the bad. The other thing about it is if one of the enantiomers is very active and the other one isn't active at all, you can say, well, we don't really care because then it won't cause any problems. The problem is as the cost goes way up. So think of it as if you have to throw out half the stuff that you make, or you have to add twice as much in to get it to the dose that you want, well, you're doubling your cost essentially. And so that's another reason why. There was a guy who worked at Monsanto years ago named Bill Knowles, and Bill Knowles won the Nobel Prize in chemistry maybe about 10 years ago. And he won it for doing something called asymmetric synthesis, which allows you to do some synthesis that gives you some selectivity around these chiral carbons. So I was fortunate enough to meet him a number of years ago. He has since passed away. He'd been retired for quite a few years when he won the Nobel Prize. But whatever you like, whether it's music, sports, whatever, think of meeting like the most famous person in that field. That's what it's like. You don't meet many Nobel Prize winners in chemistry. And the fact that this guy lived in St. Louis was pretty neat. So chiral is a big deal. The work that Dr. Knowles did around this really impacted the pharmaceutical industry. And so, like I said, pretty neat that a guy who worked in St. Louis his whole career, lived here, won the Nobel Prize in chemistry. Okay, so we talked about functional groups. We talked a little bit about optical isomers and some things like that, but all of that is traditional organic chemistry. What I'd like to do now is move over a little bit and talk a little bit about some more biochemistry type stuff. And so we're going to focus for a bit on some biomolecules. Once again, if you go on and you take biochemistry, you'll get a much better explanation, a much more in-depth explanation of all this stuff. The purpose today is to just give you some terminology so that later on, when you see this again, you'll say, hey, I remember hearing about that. I know a little bit about that, things like that. So we're not trying to make you biochemists today, but we are trying to get you to have some idea of just what some of these terms mean and what the molecules are and things like that. And so when you think of biomolecules, you tend to think of them in two ways, at least I do. One is that some are considered biopolymers. And if you think about when we talked about regular organic chemistry polymers, what we talked about was repeating units. Okay, so you have a big molecule that was made by taking little units and combining them repeatedly to make a big molecule. You're doing essentially the same thing in biopolymers. So you're taking small molecules, you're joining them together and doing that multiple times to make a bigger molecule. And that's the term biopolymer. And some examples of those are proteins. As you'll see in a moment, those proteins come from amino acids. Polysaccharides, also known as carbohydrates, those come from some sugars and things like that. Nucleic acids, once again, you have smaller molecules joined together and form the big ones. And then the other bucket, though, are some biomolecules are just big molecules, okay? It's not because of they were made by taking small molecules and doing something like that. They're just big molecules. So we don't consider those to be polymers. They're just big molecules. Okay, so let's talk a little bit about amino acids and proteins. And so for the moment, this figure you see on the right-hand side of the slide, let's ignore that. And we'll get to that in a moment. For now, let's ignore it, because that's not an amino acid. I don't want you to get confused and think that it is. So amino acids, and we'll see some examples on the next slide, but amino acids have two things that they have to be an amino acid. One is an amine group, makes sense. The other is an acid group, makes sense. And the acid group is a carboxylic acid. What's the carboxylic acid? Remember, that's our carbonyl, our C double bonded O, and then bonded to that an OH. So that's the carboxylic group, that's the carboxyl group. So amino acid makes sense. Amino is the amine group, acid, the carboxylic acid group. So amino acids have those two functional groups on them. When we make a protein, what we're doing is we're taking a bunch of amino acids and we're reacting them together. And then the end result is this bigger molecule, which is our protein. And so the reaction that takes place is called a condensation reaction. And that reacts the amine end of one amino acid and then the acid end of another one. Okay, so you have that amine group of one amino acid reacting with the carboxyl group of another amino acid. And then you form the amide linkage. Remember, we talked about amide being, and now we can look at this structure here on the right-hand side, but this is our amide linkage, or amide structure of where we have the C double bonded O, our carbonyl carbon, bonded to a nitrogen. And that amide, which we talked about before, when used in the context of these proteins and peptides, is called a peptide bond. Okay, so amide linkage, peptide bond, same thing. It's just if you're in the biochemistry world, you call it a peptide bond. If you're in the organic chemistry world, you call it amide. Okay, but it's the same thing. It's that acetyl bonded O, that carbon, that carbonyl carbon bonded to the nitrogen. So let's take a look at some of the amino acids, and there's a couple things I want to point out. What you'll see on all of these are several things. One is, as we mentioned, let's look at the first one, glycine. Here's our amine group, the NH3 there. You see there, it's positively charged. So that's a case of where we've still got one R group on it, but it's a primary amine because the other things are protons. It also has a carboxyl group. So we said it has to have that acidic carboxyl group. It's got to have that basic amine group. Every one of these on this chart has that. That's what makes them amino acids. The things in blue, okay, the things in blue boxes are the functionalities that define them as the different amino acids. And you see there's a whole range of things. Up top here, we have nonpolar things. In the next row here, we have polar amino acids on the left and aromatic ones on the right. We have some basic amino acids here on the left and the bottom, sig ones on the right. So we've got a host of different amino acids. The other thing I want to point out to you is all the amino acids have a name, all right? If you want to learn those, feel free. I don't really care about that. But if you look at them, some of them are probably familiar to. Glycine might be familiar, alanine, leucine, on down the line. But what you also see is underneath the name, you see a 3-letter designation, and then you see a single letter designation. So like glycine, for instance, over here on the top left, we have GLY, and then we have a G. What you find is when you start talking about proteins, because they're big and people don't want to write all this stuff out, they start to use these shorthand versions. Sometimes the shorthand version is the 3-letter one to designate which amino acid that is. Sometimes it's simply the G. So just be aware of that, is if you start seeing some of these bigger molecules written out, they're probably not going to say glycine, alanine, valine on the line. They might do the 3-letter abbreviation, but more likely they're just going to use the letters. And so that's why all the letters are different. So, and some of them, like you look at tryptophan, the letter is W. I don't know enough about this to know why that's W. I'm sure someone knows the history of it. Probably when you take biochem, they'll tell you. But it's kind of funny because some of it makes sense. Glycine G, yeah, I get that. But tryptophan W, I don't know where that comes from. So let's talk a little bit more about protein structure. Proteins, as I said before, are really big molecules. And because of that, what you start getting is you start getting interactions within the molecule. And usually the interactions center around hydrogen bonding. Hopefully you remember hydrogen bonding. That's that association where it's not a real bond, right? It's just an association that involves hydrogen. And so then you start getting some attraction there. And in proteins, because they're real big, they start doing folding and bending and things like that based on this hydrogen bonding. So for proteins, you have what's called a primary structure, and that's the sequence of the amino acids in that peptide or protein chain. And so you hear some people talk about we're going to sequence a protein. Well, that's what they're talking about. They're going to figure out what that order of the amino acids is that makes up the structure of the protein. That's the primary structure. But then these other secondary, tertiary, quaternary structures, now you start getting into that three-dimensional aspect of the protein. And for proteins, that's really important, okay? When you think of these biological processes that the proteins might be involved in, they usually need a certain shape for it to be effective. And that's where if you mess up some of these secondary, tertiary structure things, even though it's the right molecule, it doesn't work right anymore. So secondary structure interactions between the carbonyl atoms, the C double bond O, and the amine atoms, the nitrogen, hydrogen, and there's some hydrogen bonding that can occur, and that gives it that secondary structure. Tertiary is that there are some side chain atoms, okay? So secondary structure is interactions with the core, what I think of as the core part of the molecule, but tertiary structure would be side chain atoms. So what do we mean by side chain atoms? If we go back to our amino acids, the side chain atoms would be the stuff in blue. So depending upon which is in that blue box, you can see how you can get some interactions on some of those. Some of them not so much, others a bigger deal. So that's that tertiary. Secondary structure is basically our amide bond type interactions with other parts in the molecule. Tertiary is hydrogen bonding involving that other stuff. And then quaternary structure, that gets a little more complicated. That's when you have other stuff present and you can have some non-amino acid portions of the proteins kind of doing stuff. The primary, secondary, and tertiary are the ones that are the most common to be concerned about. Here's some cartoons about it, just kind of showing, you see this kind of stuff, which is fine, I guess. But what I would like to do is talk a little bit more about the primary, secondary, and tertiary structure. So primary structure, as I said, that's that sequence of amino acids, okay? And when we talk about forming that, let's go down to the bottom here and see our friend, the amide, okay? In this case, since we're doing biochemistry, we'll call it the peptide bond. And so that's that C double bond O, that carbonyl carbon bonded to a nitrogen. And that amide bond there, that amide functionality, that's repeated over and over. In this case, it's a pretty simple one. It's a 2 amino acid compound, and we see it expressed as gly-ala or GA. Okay, and this is where I was saying is people typically don't write the whole thing out. The most common one I would say is just the letters. So then you know which 2 amino acids, in this case glycine and alanine, are stuck together here, reacted together to form our molecule. In proteins, it's going to be a lot bigger than this, so you have a lot of these letters in a row. Once again, secondary structure, that kind of corkscrew or spiral staircase type thing is what people are used to looking. It really, once again, what you're talking about is the carbonyl in the base of the chain, doing some hydrogen bonding with the NH from another portion, amino acid in another portion of the chain. Okay, so it's hydrogen bonding within that main chain of the molecule. There's something called alpha helix and then beta sheets. Sheets is a similar thing going on. What I would remember on this stuff is in each of these cases, you're talking about hydrogen bonding going on. It's just how it kind of winds up manifesting itself depending upon what section of it is doing the hydrogen bonding and things like that. Wouldn't get too hung up on that at this point, but I would know that secondary structure involves hydrogen bonding for that core chain of the molecule. Tertiary structure then focuses on these intermolecular forces, can be hydrogen bonding, can be other things, dipole interactions, it can be ionic interactions, things like that, because as we saw from those amino acids, when you get to those other functional groups that are stuck on the amino acids, there's a whole range of groups that are there, and they're all going to have a little bit different properties. And that's what we're talking about in the tertiary structure. This is usually something that you observe when it's in water, when it's in solution. And that intermolecular of those side chains is what drives that shape. So both that secondary and tertiary structure are driving the shape of the molecule, which, as I said before, is important in how it interacts in the biological matrix for whatever its purpose is. Quaternary structure, so you have some proteins that have more than one polypeptide chain. And some proteins contain portions that are not amino acid in nature. Those kind of interactions contribute to this quaternary structure. Like I said, the quaternary structure gets into some more complex things. We're not going to worry about that. Proteins that are water soluble are called globular proteins. And then what I'd like to do now is move on to carbohydrates a little bit. So carbohydrates come from the empirical formula for sugars. And for simple sugars in that formula, X and Y are the same. When we think of simple sugars, those are the monosaccharides. And they can be drawn either as straight chains or as ring structures. In solution, they're technically ring structures. And here's another way of drawing monosaccharides down this kind of straight chain. And so the side that the OH groups are on, that matters. That tells you something about the sugar. On the left, we have glucose. What you should note on that is it's an aldehyde because we've got a carbonyl carbon and oxygen, and then a hydrogen bonded to that. So that's an aldehyde. Fructose is a ketone. We've got the carbonyl group here, the C double bond O, and we've got our groups to each side. So in that case, that's a ketone. If you have two monosaccharides together, that's a disaccharide. This is usually what we think of when we think of sugar, like the sugar we eat. On the left-hand side here, we have sucrose. Sucrose is a disaccharide consisting of glucose and fructose. So those two bonded together give us sucrose. On the right-hand side down at the bottom, we have galactose bonded to glucose, a disaccharide, and that's known as lactose. Lactose is the sugar in milk. It's the milk sugar that some people have digestive issues with. There's also polysaccharides, and when we start getting to polysaccharides, and this gets to longer chains, then we start talking about things like starch. We talk about glycogen, which is a way that animals are able to store energy. And then cellulose, which makes up like plant walls and things like that. So you get to these saccharide chains. So we started with monosaccharides and carbohydrates, the simple sugars. We start building on that to disaccharides. And finally, we get to polysaccharides. As we get to the bigger molecules, we see that there is more there's different uses, different properties of them. I'm going to skip lipids for now. Because I want to go to fats and oils. Okay, so fats and oils consist of long-chain carboxylic acids and glycerol, or they're made from long-chain carboxylic acids and glycerol. The fats will have only saturated carboxylic acids. So remember, saturated means you've got all the maximum number of hydrogens there. So those are at room temperature, typically solids. And the saturated fats are the ones that people usually consider to be bad in your diet. The unsaturated ones will have some double bonds in there. And because of that, they're typically liquids at room temperature because they're unsaturated. And you also hear the term polyunsaturated versus monounsaturated. The polyunsaturated has more double bonds in those molecules, and so those, once again, are considered more healthy than the monosaturated. The final thing is there are some essential fatty acids, and these have to be in our diet because our bodies don't produce them. And the two that you usually hear about are omega-3 and omega-6. And those fatty acids, that's the ones you get in like fish oil and stuff like that. Here's the structure of a fat. And what you always see is you see a long alkane chain here, okay? Then over to the side would be the carboxyl group. The carboxyl group gets derivatized into an ester, okay? So if this, instead of being this CH group on the left here, if that was a hydrogen, it would be carboxyl. But since we've got an alkyl group there, now it's an ester. So the way this is done is they esterify these to put an ester on, and then they react across. And you have a nonpolar side, which is in the blue box here, and then a polar side over on the left-hand side. And the fatty acid part, in this case, it's palmitic. That's a host of ranges that you'll see. Skip phospholipids for now, because I want to get to nucleic acids, and we're kind of running out of time. So when people think nucleic acids, there's two things that you think of. They either think of DNA or RNA. It used to be everyone just thought of DNA and no one thought of RNA. These days, everyone thinks of RNA because the Pfizer and Moderna vaccines are RNA-based vaccines. So RNA has gotten much more popular recently because of that. Well, what's the difference between the two? Well, there's some pretty significant differences in terms of size and functionality. So DNA molecules are really, really big. 6 to 16 million AMU. AMU is an atomic mass unit. Just think of it as a molecular weight. Okay, there's a subtle difference there, but just think of that. So think of something whose molecular weight is 16 million. That's really big. RNA, we say are smaller, but it's still 20,000 to 40,000. That's still a very big molecule, okay? DNA is primarily the nucleus of the cell. RNA is outside. And RNA carries information from DNA into the cytoplasm. DNA stores the genetic information. And that's why a lot of times you'll hear RNA referred to as, you'll hear a type of RNA called messenger RNA, because it's delivering the information. That information that the RNA delivers is used in protein synthesis outside the nucleus. Okay, so the DNA says which proteins the cell can synthesize. The RNA delivers the information to carry out synthesis outside of the nucleus. So that gets back to some of the ideas behind these messenger RNA vaccines and things like that. But when we talk about nucleic acids, they kind of have some common things. They have this phosphate unit on one end. There's always a sugar there. And then there's some type of nitrogen containing unit, okay? So they always have that. Depending upon whether it's RNA or DNA, these base units vary, okay? And so it's interesting because RNA and DNA really isn't, in terms of those nitrogen units, is made up of just 4 things. Each of them is 4 things. But because they're so doggone big, you can have almost an infinite combination of things. And so I've always found that interesting, that something that complicated really comes off of 4 things. When we talk about polypeptides, or polynucleotides, excuse me, polynucleotides, this is the general idea of what you get in terms of the connection. Obviously, we've got 4 bases here. We just said that, you know, base pairs can be anywhere for RNA, at least from 20 on up. And 20 is a really little one. Usually it's at least hundreds. And so you quickly get to pretty complicated chemistry here. And there's a lot of secondary interactions and things like that with RNA and DNA as well. The DNA, I think the most famous thing people have seen is this double helix. And what you see is you see hydrogen bonding here, and it's between those nitrogen units. And so you see over on the right-hand side, cysteine rather, and guanine, thymine, and adenine. Those are always the para. For DNA, it's always C and G paired up, and T and A. A and T, G and C. Those are the things. You won't see the G with the T, you won't see the C with the A. It just doesn't work that way. So this is what I was saying is, and these two looks like ribbons. Those are called strands. And in DNA and RNA both, you always have the strands together. There's things you can do to separate the strands. There's things you can do to put them back together. You see the 3', 5', that has to do with identifying where the phosphate group is and stuff like that. We're not going to get into any of that here. I just simply want you to know that with DNA and RNA, really big molecules, DNA is always A and T and C and G. RNA is different. It's GC and AU. And so, but don't worry about that. We're not going to worry about that. Worry about the one for DNA since we got this in the slide. And then there's these secondary interactions which kind of hold the strands together, and that's real important too. So we are out of time. So just to repeat again, here's some homework that you can take a look at to test yourself on how well you know this stuff. We'll have a quiz on this chapter on Thursday. No lecture Thursday. Next lecture will be on Tuesday, where we'll talk about nuclear chemistry for a period. And then on next Thursday, we will have, or the Thursday next week. So the Thursday this week, quiz, Thursday next week, final exam of the semester. And then the week after that, the final exam. All right, thank you.